bones, packaging, dishes, cutlery, and that. So you can characterize those things into a a light fraction and a heavy fraction. That's the way we do it. And things that have low density and high density, and how do we manage those in a multiple step process in order to remove them and to have an effectively running system with a good amount of uptime. So sorry, there's just an example of a spoon stuck in a pump, and on the left and on the right you've got the accumulation of a floating layer full of plastics and fibers in the top of an anaerobic digester. And this is a digester that deals with 100% urban waste, and well, it accumulates over time. So these are the kind of problems that we run into. And so what do we have to think about? Well, in designing a system, we have to think about what is the capital cost of this equipment, what is the operating cost of this equipment, as opposed to a facility that would just take clean organic waste. You have to think about your contaminant disposal costs. You have to think about your intake mechanical problems. You think, well, maybe I'll get, by taking in physically contaminated waste, I may have an increase in energy production. Well, that may or may not be the case. There's things, different equipment and technologies may remove a lot of organics, and so you may have a loss of energy from what you expected. And so there's a number of different levels and layers to think about in terms of managing this material and producing renewable energy. And of course, one of our largest, our primary focus is to produce a liquid slurry, a clean digestate, a clean manure type product in the back of a digester. That is essentially our goal. One of the main drivers in our finding a solution, because ultimately the economics on these projects can be make or break based on digestate management. So let's go through and quickly analyze some of the solutions. And so integration is critical. Things are not a plug and play with pieces of equipment. A lot of experience is necessary and a proven track record in the management, installation, and design, essentially, of multiple pieces of equipment in order to have an effective process that's sustainable for the long term. Another key important point is that equipment manufacturers don't design or integrate solutions. They sell you pieces of equipment. And I can tell you from experience that contaminant removal is a process. And so just buying one or two pieces of equipment and trying to get, trying to do the integration yourself, absolutely, I don't recommend that. And look for people that have a proven track record. Specifically, there's limited performance guarantees on equipment. So if you're looking to sort of backstop some of your decision-making process based on a performance guarantee, I can tell you there are many shell games that can be played in the anaerobic digestion marketplace. Many companies with a lot of marketing dollars, whether they're an equipment manufacturer or an AD company, can definitely there's a lot of tricky let's say calculations and considerations in terms of this that may it can be difficult to pinpoint what is the right solution. So and then you can say, well, maybe I'll just get them to guarantee something. But in a lot of what happens in this marketplace is someone will say, well, if you can guarantee me the feedstock quality, then I can guarantee you an output or a throughput, and we all know that's essentially a non-starter. No matter what type of conditioning or pretreatment equipment is chosen, you will get a dirty slurry. You cannot clean organics in one fell swoop. It's just not possible. And the largest, I would say, one of the most major considerations in this trying to find technologies or equipment or solutions is water consumption and the amount of parasitic energy use. There's some solutions out there that look really great, but if they're chewing up 20–25% of your energy consumption, then I would say that that's not an effective solution, and it's a long-term financial loss and drain on the financials. And as well as water consumption. And again, that also leads to increased energy consumption. And I'll explain further down the road why these two are extremely, well, particularly water consumption is an extremely important consideration. So we advocate a multiple-step cleaning process. And why do we do this? Because it's just the right thing to do. No single piece of equipment can clean organic waste enough to prevent a downstream mechanical problem. And that's just a fact. And if you try to do so, if you're pre-processing, you're doing things on the front end of a system, and you're trying to get it all out at once, then you inevitably run into a situation where the likelihood of you separating a lot of organics along with the contaminants is extremely high. And then under those circumstances, you're not producing as much renewable energy. Then why are we doing this? I think producing clean digestate is one pillar of this business. As I said, I think it needs to be a forefront for sustainability. And I also think that producing as much energy from every cubic meter or ton of material that's handled is another pillar. And if we compromise those two pillars, then we are compromising the industry in general. And then we get into this game of pushing tonnage through for the sake of it, and we're not interested in doing that. So slurries that are produced can contain significant amounts of heavy solids like bones, metal, and eggshells. Some bones float, but some bones will sink. Like poultry bones can float. Plastics will also make it through your initial pre-processing and cleaning systems. But also consider that heating during pretreatment can improve your solid separation process or contaminant separation process. So without a multiple-step cleaning process, your digester will accumulate a sinking and floating fraction inside the tank. And so here's a picture. So our system, I'll explain in a minute, actually has a tank, an in-situ interior tank cleaning system. And what you see here on the left is the grits that build up on the bottom, and on the right is the floating and fibrous, you can see it's largely film plastic type of material. And this is what comes off of dealing with the material, as we discussed before, and commercial and municipal organic fraction of waste. And so this is what you deal with. And we have an effective cleaning solution. And so what you see here is the representation of like 1 to 4% contaminants making it through, which is what we do on purpose. And then we clean the tanks on the inside. But this is what gets through. So when people say, "Oh, I'll let 1 or 2%," oh, it's no big deal. I completely disagree. It is a big deal, and you end up trying to play catch up downstream. And we'll discuss this a bit more coming up here now. So just a quick, explanation as to how we get that sediment and floating fraction of the picture I just showed you out. So we have an in-tank contaminant removal system, so it's a floor scraper. And this is what we use. It's a continuously operating system, and it sweeps the floor of all the grit material on a cycle, and the cycle is determined as to from the initial auditing and sort of post-commissioning auditing of the waste and how it's being processed. And so you have your digester operating 24/7, 365 for decades. And we also have, so that's to take out the sinking fraction that's resultant from pre-treating a slurry. Then we also skim a fraction. So this works in the unique design that we have on this is that it works in a gas-tight environment. So it's safe for that. And we are able to skim continuously the floating fraction off the digester. And essentially all the digestate from the tanks that pass through this skimmer and a filter. And so essentially every cubic meter that's put out of our system is essentially 100% clean. There is obviously still some grit fraction in there, but visible plastics are all removed, and you're into a small amount of grit, which is, sand and particles like that at that point. So in order to try to do, like, looking at all this, like, what options should we consider and what should they accomplish? So now I'm going to talk a bit about some of the technologies, let's say, that are out there, and so give it just a general description as to what they may be and what we need to do here. So what is pretreatment? So pretreatment performs multiple functions, from package opening, depackaging, you could say, particle size reduction, to separation of organics from the contaminants, as well as to move slurries throughout your plant. So there's some common technologies, common equipment, let's say, that are deployed to do this. There's horizontal and vertical shredders. There's press-type pumps, which we use. There's separation mills, also known as hammer mills, hydrocyclones and hydropulpers. And kind of unique to the marketplace, of course, we have this in-tank cleaning equipment. Common to the market is heating and pasteurizing as per regulations. But not only are they pasteurizing, but they also can be utilized if inserted in the process to aid and help improve the filtration process from the plastics. So I'd mentioned that, going through this list, there's increased water consumption. So I'll just put out the so you guys can read through this as I talk. So one of the main considerations in all of these equipment have a total solids working range, and of course you have feedstocks that have a range of total solids. So looking at what your plant is going to process, what feedstock contracts you have, what is this material, and trying to match the right technologies for the right solution to match the feedstock that you're going to do, to minimize things like water use, electricity, parasitic electricity consumption, and water is the big one because it costs you to purchase it, it costs you to pump it, and it costs you to dispose of it. So what are we looking to achieve? So we're looking to achieve a balance between water consumption in use, in separation, and losing organics with your solids. So you can use less water, but then you may lose more organics in your overs. And so this is the crux, or this is the knife's edge, as it were, that we try to balance in this business. So the more water could also mean a lower retention time. So let's say, for example, you want to take pre-processed material at a facility, or you intend to utilize a pre-processing on site. You need to think about how big your tanks are, because if all of a sudden you're adding 50% water to your feedstock, and you're adding 50% water to your feedstock, all of a sudden now you have this volume, and what are you going to do with it? Yes, you can recirculate some of your digestate and remove some of the water, but essentially you have an increased water use, and you can lower your retention time if you have a fixed volume, or it could mean that you have to build larger tanks, and which both of those things add cost to your system. So there's smaller screen sizes. Generally, whether it's a separation mill or any of these technologies are equipped with screens, and the processes of generally the concept of contaminant removal is all about density differences, increasing the density difference between the organics and the packaging, and using the equipment to separate it. So smaller screen sizes, 1 to 10 millimeters, let's say, which is about a range there, result in more organics being separated along with the contaminants. Larger screen sizes use less water, though, and so it's better for batch processing and package separation, but it will also let more contaminants through. So here's the fine line that we try to, the balance in getting the right system in place to produce clean digestate and reduce mechanical, or eliminate mechanical problems. So, why do we care? Why do we care about contaminants? Obviously, there's the one side of it where you have your mechanical problems, but you could say, well, why don't we just shred everything up small enough and make sure it's small enough, and we can just get it in our digester, and we can we'll just, I'm sure it'll just get pumped out, and we'll be okay. Well, in fact, there's a couple things that happen. So aside from the potential for the floating layer, so what generally happens, to backtrack for a second, is that you end up getting some basically whatever total solids you work with, you digest. And so let's say you put in 10%, digest down to 5. You're going to get a percentage of your feedstock is going to decrease. You're going to release water from cells, and therefore you're going to decrease the total solids inside your digester. A fraction of this material floats, and a fraction of it's going to sink at any given percent total solids in situ. So the sinking fraction will effectively, both of the fractions, the sinking and the floating, occupy volume. So how it erodes your profit margins is that you eventually you from day one, if you're not cleaning the tank inside, you're effectively losing digestion volume, and we sort of call it capacity degradation. So you're losing capacity, losing volume with which to actively generate energy. And so, so this becomes a concern. So I just ran over, and you can see here just a quick calculation as an example of if you have, if you're processing 5,000 tons a year, and 2% of it is sinking material. You've estimated this, or you have experience with it, so this is not an unrealistic number. It's saying 2%, so which equals 100 tons per year. So you think, oh, I have a volume. That's 100 tons of material. Just to start to get your idea, get people thinking about, well, quantifying. If you can quantify these potential risks, then you can begin to understand them a bit better. So let's look at their bulk density, and then how much. So if you have 62, say, well, is that really a lot? Well, there's a standard size digester we see around as a 1,500 cubic meter tank. So on a 1,500 cubic, most common there's larger, of course, but a lot of common size ones for about 500 kilowatts have two 1,500 cubic meter tanks, or one 2,000 or 2,500 cubic meter tank. So this gives you just some ideas. You can play with the numbers as to what kind of volume it's going to occupy per year. So I mean, you can quickly see that even being conservative, you're 4% per year of 1,500 cubic meters, and that's significant. So after a few years, I mean, sure, you might not notice that in year 1 or year 2, but after 5 years, you have a problem. And as well, the same with the floating fraction. And in fact, the floating fraction is more problematic because it gets in the way of mixers and propellers and other mechanical equipment, but it actually occupies more volume because it's less dense. And so aside from preventing gas and floating mats and other things that can relate to biological problems, you essentially have. So add these two together. I mean, you can say, you play with the numbers, you can double it, you can cut it in half, and just get an idea on your volume increase and calculate from there, which we do regularly for people, is to say, okay, well, what's this going to cost me in terms of loss of revenue from electricity production? So then you might think, well, so now just to talk about, so that's on the contaminant side. Now we can talk a bit about water use. So so if you have equipment, let's say use an example that you have 1,000 kilograms of feedstock. I should say feedstock, not substrate, but that is 20% total solids, including the contaminants, let's say. Then your hammer mill, let's say you've chosen this as a piece of equipment, this is just an example, has an input maximum functional operating capacity of 15% total solids. This is what you're looking at, about half a cubic meter of additional water to go from 15 to 20 to 15%. So you have to dilute down in order to get effective production. And often, as a matter of fact, just specifically to address these hammer mill type systems, they effectively are a lot lower than that. Their total solids can be down effective range of 9 to 10%. So now you're even doubling that. And we see this. I mean, this is, you go visit enough plants, and you find this out. And when you're looking at the second pretreatment option, let's say you're going to use a hydrocyclone, which requires a lot of water consumption. For example, its effective operating capacity is around 10%. So if you start at 20, you've got to essentially use 1 cubic meter of additional water for every ton in. And this greatly affects your energy balance, and it affects what are you going to do with all that additional water afterwards? Essentially processing water which has no energy content. So again, I'll just lay these out here so we can. So this is just kind of a summary. So what does it mean? So if your digester is filling up with contaminants and faster, and also I should add that the more water you use, it actually drops your total solids faster, and so you're going to have increased settling of the grit fraction and separation of contaminants as well. So the tipping fee, so you can have tipping fee revenue losses during downtime for cleaning. So these are kind of the considerations of, well, okay, so my digester, so now you can take your number, let's say you have 2% a year or 5% a year, whatever number you'd just like to, so do a high and a low estimation based on a good feedstock audit. What's this potentially, how do I calculate where my costs are? What's this going to cost me to close my digester down, or how can I calculate out its cost? So then we consider sort of tipping fee revenue when you have to shut down for cleaning. You have to disrupt the feeding process. So you have a loss of tipping fee revenue. You're not bringing in any material, and so you don't have that. You have energy losses because you're shutting down your system at that time. You have you also, it's not just your downtime. Remember, it takes 1,500 cubic meters doesn't get filled. That's a small digester. That doesn't even get filled overnight. So you have to think about your ramp-up cycle, and you're not producing 100% gas, so it may take you a couple of months, realistically, to get back up to 100% again. So you have your loss of revenue during that time, and your decrease in revenue for tipping fees and everything else during that time. Plus, you've got the labor costs associated to remove the contaminants from the tanks. So really, the labor, you have to get people in the digester. It's not cheap. You can't empty it 100%, and you need like sort of vacuum trucks or pump trucks to get the material out. People have to get into this environment. There's still hydrogen sulfide being produced, so the labor costs associated with it can be a lot greater than people really think at the end of the day, and it generally takes longer. The other part of that is that that over time, that grit becomes a hard cake, hard mass at the bottom of the digester. So oftentimes you may have to drop a mini excavator or a bobcat or something in there in order to scrape it out, which complicates the problem again. And then further complication is if you have a digester, if you made a digester with a steel tank, you can't do that because of the risks of damage to the enameled steel and everything, which is one of the reasons why we use concrete. We don't even risk designing a digester with a steel tank. Yes, it may save you money, but ultimately, especially if you're dealing with this type of feedstock, I really don't recommend it and wouldn't do it. I would invest in it myself. So now just a quick discussion on the financial implications for high process water consumption. Again, increased energy use for purchasing and pumping extra water. Potential decrease in retention time or requires larger digesters, increasing capital costs. Increased treatment and disposal costs of the extra processed water. Again, you can recycle some water, so recycling digestate, but it can only be done to a certain point. Generally, the limiting factor is nitrogen load, and if you've got a lot of meat or high protein material in your feedstock, then you may not be able to recycle as much as you thought, because you will ultimately have an accumulation of nitrogen, and so there's a limit based on the nitrogen balance of what you're trying to do here. So again, in summary, I'll just lay it out here and then can go over them. Successful integration of components is required for a properly operating plant. Include buffer capacities in processing. Again, just looking at a design, you've got 4 or 5 pieces of equipment. Well, I shouldn't say 4 or 5. Let's say 2 or 3 pieces of equipment, and you have to think, well, I have to move something from A to B. How do I buffer the volumes, and where do I add water? Where do I mix? What's the best way to do this? It requires a proven systems approach. You need to be discussing, if you're considering to do this, you be thinking about how to who's done this before and successfully done it for the long term. Also think about long-term financial and operational success. At the end of this presentation, be going, oh my goodness, well, why does anybody take this material? It's the same reason why composters take this material, because it's challenging and garners revenue. And so it's the same reason, and it's actually the highest energy yielding material, well, not the highest energy yielding material, but a quite high energy yielding material in terms of for the anaerobic bacteria. And so this is obviously why we do it. But you have to calculate and factor in the financial implications of managing this material. And that's really what we're trying to do here is try to do to everybody is to point out, look, here's all the risks, here's the benefits, there's a downside, but there's an upside. And as long as you can characterize and identify them properly for somebody, then you can begin to make intelligent business decisions and intelligent technology decisions and let's say business partnership decisions that benefit everybody in the end. And of course, to produce clean digestion, I can't emphasize this enough, that along with producing the maximum amount of energy from every ton of material you handle are essentially the two pillars that we operate on and that I promote in the industry. Oh, and of course, to minimize digester downtime. The difference in profitability between systems that fail financially and the ones that are successful are the difference between one person that's operating at 90% and the other guys at availability, and the other one's at 95% or 94. And that you know, relatively, whether it's 80, 85% or 90, it doesn't matter. That extra 5% that your neighbor's doing, that's where the money's being made, and that's what's really adding up to your payback. So that's where you make your money on these projects, and successfully and for the long term. And so it really is sort of the thin edge of the wedge in that sense. So there's my contact information. Of course, you can contact the Compost Council to contact me, or email me directly, or call me. Very happy to talk to anybody or answer further questions. I guess we'll probably do a question and answer session now, Addis?
Yes. Can everybody hear me, I believe? Thank you, Tom, for the presentation. And thank you everyone for your attendance. We apologize for the technical problem we had earlier. We appreciate your patience. So now we'll go to the question and answer session. We have a few minutes before we wrap up. If you have questions, you can click the hand button, and I'll unmute you so that you'll be able to talk, or you can type it in the chat dialog box, and I'll read that out loud. So you can.
Yeah, Addis, I think you may be the only one to see the questions. So.
Yes, I don't see any questions, but let's give people a few minutes.
I mean, that was really a sort of a high-level overview.
Yeah.
I can do a more detailed. You can separate out sort of the pre-treatment processes and digestion processes and consideration for those sites in more detail. So if anybody would like that, maybe if they, there's something specifically that people want addressed or would like to have more details on, then I can tailor my next presentation in terms of that.
So I think we don't have questions from our attendees.
Okay.
Yeah.
So, okay, so if that's the case, then thank you so very much, Tom. Again, we're sorry, everyone, for the technical difficulties. We're not sure exactly what caused that yet, but we'll have to try and figure that out. But thank you very much, Tom, for making yourself available, and thank you, everyone, for joining us. We'll be sending information on our February event very soon. We don't have it organized just yet, but we will be in the next couple of weeks.
Okay, great. Thanks. Everybody have a nice day.
Thank you.
Thanks, everyone.
Bye.